So let me talk about conditional probability density functions. We know a probability density function actually describes everything about the random variable. Probability density function is a non-negative, so any function in fact which is non-negative, only two properties, and the area under the function is 1. So this is a density function. So physical meaning being so this is a non-negative function, and if you integrate everything, let's say it adds up to 1. So of course the function has to die out because of the finite integral. And the meaning is that if you take any region, this area, which is the area from x1 to x2, let's say this is x1, this is x2, then this shaded area is the area under the density function over that region. And as we know, that's the probability of the random variable taking values in this region, x1 to x2. So that's the physical meaning of this density function. Now we want to update this information in case some other event occurs. So to do that, we go to the definition of conditional probability. So we have PA, and then we have probability of A given B, where given B. So that's going to be by definition PAB over PB. So we want to make use of this to update the information about. So remember, so similar, any density function also has a distribution function. This is more, a little more physical. That actually describes all the probability of the random variable taking if this is x, all this probability, any value less than or equal to x. So that's this probability. Of course, this is also the area under the density function from minus infinity to x fx under this function. So the question is it possible to update this given some other event? How do we define this? So fortunately, we can use the conditional probability because after all, the distribution function is the probability of some event. So if I call this to be A, so fx of x is probability of x less than or equal to x. So if I call this to be A, so this is like, or AX rather, so this is probability of an event. So if I want to introduce the notion of conditional distribution or conditional density, then you can see it makes sense to go with, this should be helpful to us because distribution function is after all the probability of an event which depends on x, which is the variable here. So this is, we should be able to write it like this. And this is well defined. So this is going to be probability of AXB over PB. But AX is now probability of x less than or equal to x intersection with the B over PB. So now depending on what B is, you just need to simplify this. And since all the definitions, since we have done this properly, this function will have all the properties of the distribution function. For example, when x is minus infinity, you can say this is the null set, so the whole probability is 0. When x is plus infinity, this is the whole set, so this is PB over PB, that's 1, etc. And non-negative, all the properties. And if you, the derivative of this should give us the conditional density function. So is going to be, the derivative is of course with respect to the running variable. So what is the use of this? So we can also use this to compute the, for example, we know that the probability of x being greater than x1 and less than or equal to x2 is the distribution, ordinary distribution function or which is the same as x1 to x2 fxx dx. So question is, so this is an event after all. Can we do this? What would be the conditional probability of this given B? So if you treat this as A, as I said, this of course reads now AB over B. So this is probability of x greater than x1, greater than x1 less than or equal to x2 intersection with the B over PB. But to simplify the numerator, we can look at this way: x less than x of x2. Let's say here is x1, here is x2. So x less than x2 is, of course, we can write it as the disjoint union of this way, right? It's this set and this set. So now if I intersect it with B, because I want to compute this quantity, so these two are mutually exclusive. Now I'm going to do intersection with the B here. So I'm going to do, that will be intersection with the B, but this is union like sum, so there will be a B here and a B here. So now if I take the probability of this side is the sum of the probabilities. So probability of this piece is going to be intersection with the B is probability of this minus probability of this. So that's going to be probability of x less than or equal to x2 intersection with the B minus probability of x less than or equal to x1 intersection with B. So let me substitute that here. So this now, because that's the numerator precisely. So this is now probability of x less than or equal to x2 intersection with B minus probability of x less than x1 intersection with B over PB. So I can write it like this. But now we are back to conditional probability again, because this is like AB divided by PB. So I can write this as probability of x less than x2 given B minus probability of x less than or equal to x1 given B. But that is fx of x2 given B minus fx of x1 given B. And since fx, capital Fx is, or the other way from here, the capital Fx of x given B is the integral of fx u given B multiplied by, so it's just the integral. So that's going to be fx u given B du minus infinity to x. So we can also write this, if you want, to be x1 to x2 fx x given B dB. Remember, the variable is x. So let me show all right. So this is as far as the theory goes. Now the question is how useful this is. So to illustrate, first of all, let me do a couple of problems to show you how to get the conditional distribution function. And so a formula that I want to save is, I'm going to copy it here. So we have probability of Shall we do it for a couple of specific A's and B's? Specific B's, in fact. So let me do two problems. Let's say X is, let's say B is this. So the question is, we have a PDF of X, and we have a density function of X. These are the original ones, unconditional ones. Of course, this is goes up to 1, etc. Now, B is given to be this. So the question is, what is the conditional density, what is the conditional distribution function of X given B, and also what's the conditional density function of X. So we can use this formula here, right here. So the conditional distribution function of, so first of all, conditional distribution function of X given B is probability of X less than or equal to X intersection with the B over PB. I'm just copying this formula. So remember, X is all the variable, but you see that there is an action happens at A, so I'm just going to mark the point A. So in this case, what is given is a random variable only takes the values. It is given that the random variable only takes values less than A. So if that information is known, how do you modify this? That's the question. So we have one case of interest is X less than or equal to A. Other is as a function, I need to find out for X less than or equal to A and X greater than or equal to A. So I'm going to take X to be somewhere here to start with. Then notice in this, so you have two events here, or two sets here, X less than X, which is the probability of something gets mapped here, intersection with B. So X is, or let me also substitute for B. So this now reads probability of X less than or equal to X, intersection with X less than or equal to A, over probability of X less than or equal to A, because B is given to be X less than or equal to A. And now, as I said, I'll draw it here separately. So let's say A is here, and let's say X is here, because I'm going to take the case when I'm going to do two cases. Let's say X less than or equal to A and X greater than A. So when small x is less than or equal to A, I mark here. So this, so look at here, you need the random variable being here, that's X less than or equal to X. Intersection with the random variable being less than or equal to A, that's here. So the intersection of this is, you can see, the intersection of these two sets is X less than or equal to X. So the numerator is going to be probability of X less than or equal to X divided by, this is by definition distribution function of X evaluated at A. And here, so here of course, the second case is X is here, A is here. Second case is when, so this is the case when X is less than or equal to A, this is X greater than A. So if X is greater than A means in this case, X is beyond this here. So the numerator is X less than or equal to X, which is this up to here. And this second term is X less than or equal to A up to here. So their intersection is X less than or equal to A. divided by, but that's fx divided by probability of x less than or equal to a. So this is 1. So this is fx of x divided by fx of a. So that's the answer for the distribution function. And the density function is the derivative of the distribution function. So the conditional density function is going to be d by dx of fx of x given b. If you do this one, then it is easier. So this is easy here because there is only x term here, so that the derivative of the distribution function is density function, small fxx, divided by fx of a. That's a constant. Derivative of 1 is 0. So this is for x less than or equal to a. This is for x greater than a. So now we can draw it. So it looks like this is just a, whatever is this shape, it's just a scaled up version. So it goes like, that's the distribution function from here. And here, this is a scaled up version, but so that at here it becomes 1. So also a scaled up version. But this value is already 1. And then of course it stays 1 because the distribution function is non-negative and non-decreasing. And it already attains the value 1, so it stays 1. So let me do another example. So let's say in this case b is given to be, the random variable is known to live between a and b. So this is the information given to us. The random variable only takes values between a and b. And once again, what are the conditional density functions and distribution functions? So this is fxx, this is fx of x. So again, quickly we can just use the same formula. So once again, the conditional distribution function is from here, probability of x less than or equal to x, intersection with the b. So let me just write the b here. B is given to be this, x greater than a less than or equal to b, divided by probability of x greater than a less than or equal to b. Now, probability of x greater than a less than or equal to b, I mean, this, the event that x is greater than a and less than or equal to b, the best question is what is its probability. So to compute this, as I did before, we can write this as if b is beyond a, let's say a is here, a is here, b is here. Okay, so obviously b is beyond a. One number has to be larger than the other. Then we can write this as in this manner. And these two are mutually exclusive. So the probability of this is probability of this minus probability of this. That's the distribution function difference. So probability of this is going to be fx of b minus fx of a. So now in here, so that's the denominator. So the denominator is going to be fx of b minus fx of a. And to simplify numerator, I'm going to intersect here with x less than or equal to x. So I should do it on the right side also. X less than or equal to x intersection. So if I expand, this now reads x less than or equal to x intersection with x less than or equal to a. The whole thing union with x less than or equal to x, x between greater than a and less than or equal to b. So this identity is true. So if you take again, this and this are mutually exclusive because these two are mutually exclusive. So this and this are mutually exclusive. So the probability of this event is the probability of this plus probability of this, which is what we want on the numerator. So the numerator probability, I'm just going to copy from here, is the probability of x less than or equal to x intersection with x less than or equal to b minus probability of x less than or equal to x intersection with x less than or equal to a. So let me write it as two terms. So we have probability of x less than or equal to x intersection with x less than or equal to b minus, I'm just copying it here, probability of x less than or equal to x intersection with x less than or equal to a over fb minus fe. Anyway, so that's clear here. Now of course we have to go through, we have to draw the, so this is fx of x given b. I'm going to open up this space to draw the diagram. So we have to draw the corresponding diagrams here. So notice that to proceed, notice that there are points of interest. X could be, as a function, we should draw it everywhere. So this is one region, this is one region, this is one region. Again, depends on the problem. So remember, this is after all a function, so it needs to be drawn for all values of x. So I see that I need to do it for x less than a, then x between greater than a but less than or equal to b, then x greater than b. There are three cases of interest in this case because b is given to be, b is here. B says that the random variable lives here. But as a function, we need to draw for all values of x. So this is the case where you have a here, b here. The random variable x is less than or equal to, or x is, the variable x is less than a. So variable x is somewhere here. So now if you look at here, you need the intersection of this and this. So the random variable x less than x is this. The other one is x less than b. So that's going to be this. So their intersection is x less than x. So fx of x given b. So in the numerator, it's going to be intersection of this and this is going to be x less than x. So probability of x less than or equal to x. And here, again, the same thing because x less than x and x less than or equal to a. So this is also probability of, so that's going to be probability of x less than. The second term is going to be like this, right? A is still here, b is here. So here, a is here, b is here. X is, we are dealing with the first case, so x is less than a, so x less than x and x less than a, so that's this. Their intersection is x less than x. So the two terms are, it doesn't matter what the denominator is, so this is fxb minus fx, so that's 0. So now let's do the middle case. A is still here, B is here, but the small x is here. So the same formula, fx of xb. So here, x less than x, so which is going to be the random variable less than x from here, and x less than b, which will be this. So the first term is going to be, the intersection is going to be probability of x less than equal to x minus here. So you have a here, b here, x is here. So x less than x, intersection with x less than a. So their intersection is going to be x less than or equal to a. So that's probability of x less than or equal to a divided by pb over p. Fxb over fxa minus fxa. But the numerator is fx of x minus fx of a divided by fxb over minus fx of a. And the last case is again the same thing, x given b. And in this case, a is here, b is here, but x is beyond b, so x is here. Now you can quickly see if the x probability of x less than x is this set, intersection with x less than b, which will be, say, let's say this way. So that's going to be just x less than or equal to b. So the first term is probability of x less than or equal to b minus. So you have a here, b here, and x is here. So probability of x less than x, intersection with x less than or equal to a. So their intersection is x less than or equal to a. Divided by fxb minus fxa. But the numerator is exactly the same, fxb minus fxa. So this is fxb minus fxa divided by fxb minus fxa, which is 1. So if you want, I will write the answer here, is going to be 0 if x is less than a. It's going to be fx x minus fxa divided by fxb minus fxa if x is greater than a and less than or equal to b, and is 1 if x is greater than b. So of course, if you take the derivative of this, you get the density function. If you take the derivative with respect to x, there is only one term here. The derivative of this is small x. The derivative of this is constant. So this is going to be simple. And the denominator is a constant, so that stays as it is. So again, we just have to solve the given problem. This is for x greater than a, less than or equal to, and 0 otherwise. So we can finally plot it below the other graph. So notice that this function is 0 up to here. Then it is a scaled and subtracted function. In other words, you subtract whatever is this value from there. So it's going to be because at x equal to a, it starts at 0. So it's going to be going like this. But by the time it reaches b, if you put x equal to b, this is 1. So this is already reaches 1. And then it stays the same. And here, basically, it's a scaled version of this, but jacked up by the denominator. So it's just going to be a formula like this. Exactly the same shape. But the area under this is 1, because if you integrate this from a to b, this will come out to be fxb minus fxa divided by the same constant. So this area is, of course, 1. So this is a density, legitimate density, but it's a conditional density function. So what has happened here is that given that the random variable is known to live here, then this unconditional density function gets modified in this fashion, or the original distribution function gets modified in this fashion. So this is updating our ignorance or knowledge about the random variable, given that it is supposed to live between A and B. It is known to live between A and B. Let me do one more, maybe a more serious example. Let's say we toss a coin, we get a coin, so we have no reason to assume it is biased or otherwise. You keep an open mind. But the coin could be biased. So if P represents the probability of head in a toss, and P is a random variable because we have no idea whether it is biased or unbiased. So a non-prejudiced observation would be treat this as a random variable, and since we have no information, we could take it to be uniform. So this is at the beginning of beginning, where no knowledge is given. But if you say the coin is the probability of getting a head is half, then you are already biasing yourself because you are without any information. You are making a prejudiced observation, saying that it's already half. Maybe true, maybe not true. So we will perform an experiment, and so we'll toss the coin n times, and of course you are going to see a certain number of heads. Let's say k0 heads are observed. So this is a specific sequence, because it will be something like this if you do the experiment, depending on what happens there. So you start counting head as 1, 2, etc. Ultimately, you see that you got, on the other hand, if you count this 1, 2, 3, we did n tossings, but we got k0 heads on a specific sequence. So let me call this experiment to be A. So A is this experiment. Here the given coin is tossed, and so we know that it has a certain P. Only problem is we just don't know what the value of P is, but there is a certain P. So probability of these tosses are of course independent. So the probability of getting this head is P. This is an independent toss. So in a repeated experiment, the probability of this whole event is the product of the probabilities, because these are independent events. Probability of head is P.